Recording in progress.
Okay. Hi, everybody. Good evening. Hopefully you're doing okay. I'm gonna, if my Zoom, if my Zoom does kick me out here, possibly I will just stay on my iPad if that keeps me on, and I'll join the audio and just forget joining the Zoom on my computer. However, I will say it means I won't see the chat. I'm not going to be as savvy then because I can't, from my iPad, I can't be writing on it and have the chat up and all of this, right? So just keep that in mind. Hopefully no issues. And, the dogs did just go out. So let's also hope they're tamed for a moment. So let me just, excuse me. Let me get my notes up here. So get my pen on. And hopefully the homework and things are going well. Nothing was due today. I actually don't know when I made the homework for this week due, but this week is going to be on, it's covering 4.4, 4.5, and 4.6. So all three of those sections. So I probably made it due on Sunday, like normal, like it was back in the day, right? When we started, I guess. But if, anybody is having trouble, or if they notice the due date and they haven't gotten to it, or whatever the case, just shoot me an email and I can go in this weekend and update that. And I'll be grading this weekend. So I'll be on because I have exams from my other class. So super fun. And they are not as nice as grading your exams. So I will thank you guys because, your exams are so much nicer. And it's not because you're virtual, because I actually prefer like a paper exam. It's faster. Like I'm faster at grading that. However, this class is just difficult. Let's just say the students are having a lot of difficulty. We'll leave it at that, right? Okay. So
what class is it? If you know.
What's up? What is it?
What is the class? What is the course?
It's business math. So it's business math. So
business math. Oh, okay.
Yeah. It's
business math sucks.
Okay. Yeah. Okay. See, so some people know, but like it's weird.
So it's like annuities or calculating.
Well, no. They even took out most of the business. It's like really just pre-business math, kind of like this particular class I'm teaching. It's like the prereq. If they didn't make it to like they didn't pass the regular prereq, this is like their math prerequisite. So I thought it would be. I thought pre-calc was going to be more difficult, but actually, in terms of like how this for the students, but you guys are actually doing well. And not that they're not doing well, they're just having trouble. But anyway, I digress. Yeah, here we go. So those tests, needless to say, will be not so fun. But maybe they'll be nice. Fingers crossed, right? It's a 50-50 shot. So today we're starting with exponential growth and decay and models for this, right? So we're going to have some weird notation possibly, but it says let y present the initial value. So instead of like when we had that compound interest, or if you think of this type of thing, those are exponential functions as well, but we always had p for our initial value. Now we're going to have this y naught that's here, right? And think of that as the value when the time is 0. So if this is like exponential growth or decay, and we're saying, oh, it's growing or decaying, some plant or some bacteria or something is growing or decaying at this rate. Well, that means at 0, at time equals 0, the start, y naught or y sub 0 is our original value. And then, and the equation that we see is this here, this y equals y naught times e to the kt. And we see that our exponential is back, our like E value, right? So this we can typically, what you're going to be asked for these problems is you're going to be asked to find y naught maybe and find k. So finding k, we'll need to use logs, and finding y naught, we'll just have to do some calculation, right? So what this says here is for a positive constant K, this model is growth. And for a negative constant K, it's decay. So, I mean, this is saying growth, K greater than 0, decay, K less than 0. And K is never equal to 0 because otherwise this is not an exponential function, or it's not interesting, right? So these are just kind of the facts to get us started. So now we look at problem 5, and again, oh, there is an A and a B. Okay, I thought there was no B, and I'm like, we keep doing this A, and then there's no B, but that is false. So according to a study published in 2012, okay, again, we're a little bit outdated here, right? These notes, this textbook is also, everything is probably just a little bit old, but 2012 isn't too bad, right? It's not like 1995, like, okay, that would be quite outdated. But this study published in 2012, Burmese pythons. Now, these are snakes, right? I'm so not into this, just like the cockroach fan thing. But okay, we'll go with it. Pythons, they're becoming a new top predator in the Florida Everglades. Good thing we live in Texas, right? I don't know. So not many animals in the Everglades can stand against a python that can grow 23 feet. This just is scary. And weigh over 200 pounds. Like, that's absolutely ridiculous. I mean, it's just crazy that a snake is that long and then the weight of a large human, right? So wild. 20 pythons were recorded as captured or killed in 1995. Okay. And by 2009, that number's increased to 378. All right, we're saving humans maybe by doing this, right? Although I'd rather have all the mosquitoes in the world be dead than like snakes, but you know, the other day, this is a tangent, but the other day, I think it was my mom sent me an article that like mosquitoes, it was some article, I don't know if it's a good source or not, but it was, mosquitoes do have like a type. They tested, this article had a study. Like, I don't know if you're this type of person, but I'm the person that we're outside and I'm the only one getting bit by mosquitoes. And I have 20 bug bites in 5 minutes and no one else. Everyone's like, yeah, I'm fine. But there was a study that your skin, something about the oils that are produced on your skin put off a scent or some type of smell or something that the bugs like, and they're attracted to it. So what they did was they had different humans they tested their skin for this oil, whatever it was. And then they had them wear like tights or socks or something on their legs for, 10 minutes or whatever it was. Then they took them off and they put each set of tights in a little area and set mosquitoes into it. And they all went to the ones with the high, whatever it was. And again, I can't remember, but that has to be me because my life is horrible around mosquitoes. So, and like, there's also funny, I mean, okay, this is total tangent, but there's also like funny videos that people send me sometimes about people saying, oh yeah, bugs love me. And they're like making fun of people that say that, but it's like, no, this is real. And there's a study and these mosquitoes, they love me. Like, they only want to bite me and they take so much blood and it's horrible. Right. But anyways,
I remember seeing something about mosquitoes being like trainable, like you can, because the air pressure, if you just like wave them away, they'll eventually just learn to go away. You don't have to.
Okay. Well, I need to apparently do that around my entire skin so that just keep lightly waving. Yeah. All right. That is so funny. Okay. Well, I mean, granted, yeah, this study was interesting and, helped me prove my point of, yeah, they are attracted to my legs, not yours for whatever reason. But anyway, at least, okay, snakes, this is a whole nother, right? One mosquito bite versus a snake snake could be deadly, right? So here, well, especially these snakes, it seems like they're top predators here. So what the question is asking is to write a function of this form. So again, instead of y equals y naught, like we have up here, they're just doing like p of t and p naught, same thing, right? E to the kt. So write this equation to represent the number of pythons captured or killed t years after 1995. So 1995 is our base year. So what they're saying is t equals 0 is 1995, right? And we had, what was it, 20, wait, where was 1995? Oh, 20. Okay, they didn't write it. They wrote it as a number, so that, or as a word, so that was confusing. But so P naught then is the initial value, and this is going to be 20 pythons, right? Were captured and or killed. And so then they gave us another 2009, 378. So then we know that P equals 378 pythons in 2009, which is, so T would be 2009 minus 1995. Okay, maybe I should write this somewhere else. So in 2009. And so T is going to be then, what is that? 14 years, right? So 14 years. It's really easy when the starting year is like 2000, because then it's like, oh, 2009 is 9 years. Like, but okay, that's not too horrible. We started at, so our first point was 1995. Then our next point is 378 in 2009, right? So, so we have, like, you can think of it this way, like you have some ordered pairs, but instead of like getting the slope and then finding the equation, we're just going to say, okay, P we have equals P naught e to the KT. What we want to find, in this case, they gave us everything except K. So they give us P naught. I mean, T stays T because that's like our X variable, right? They gave us this P to help us, this T to help us find K. Because really all you need for an equation, like this is you'd basically have P of T equals, you need the P naught, which in our case, we actually do have is 20, and then E to the KT. Once you find what K is, this equation is set. Because if someone said, okay, what do they expect in 2030 or something, right? Or this year, we could predict what they did this year in 2022. And all you have to do is plug in that time and you can find P of T, right? So we need to figure out K. So in order to do that, I'm going to take the ordered pair here and plug it in. Or I'm thinking of it as an ordered pair, but it's really just, okay, T is 14, P is 378. So I'm going to take 378 and get 20 E to the K times 14, or maybe it's better and nicer to write 14K, right? So first I want to get E by itself. And I'm just seeing these comments in the chat because I'm slow, but you're the opposite. I'm jealous of you, David. And you're like sugar for mosquitoes. Yeah, Paul, I feel that. Okay, so we divide each side by 20, right? Divide by 20. And granted, we might get decimals here, or we will, right? And that's okay. So I get like 18.9, and it's going to be E to the 14K. So again, you can use log or natural log, whichever you prefer, but I'm a natural log fan, especially because we have this E here. So I'm going to take natural log of both sides, and then I get ln of 18.9 equals, and I'm going to bring this exponent in front. I'm not a step here. I'm just doing it maybe quickly. So if you're lost, let me know. Otherwise, we'll keep trucking. And remember, natural log of E equals 1. So this is just 1. So it basically goes away because times 1, right, goes away. So we're left with this kind of nice thing. Well, nice-ish, right? So I have ln, I'll just rewrite it up here. 18.9 is 14K. I'm going to divide both sides by 14. Cancel that out. And then I just get K all by itself. And okay, what did I get? We're going to round again, but I just rounded, I think 2 decimal places was sort of fine, like 0.21, right? So I get about 0.21. And so what I'm going to do here is now my final answer, and maybe I'll just continue it this way. So K is this. So I wanted to get this equation, P of T. I get P of T, and you could just write P, but they asked for P of T. That's fine. Is going to equal 20 e to the 0.21 t. And this is our equation. And if you want to write if you want to write this whole 0.21, I mean, that's also fine, but I just did 0.21.
Hey, Professor. So it's all right if we round like before the final answer?
Yeah. So in this case, it's going to be fine if you round, because we're not looking like, if you're rounding early, it's not really affecting, it will change your answer slightly, but we're always going to round for this type of stuff. So yeah, if you didn't leave, like, you know, if you wanted to leave this as a fraction the whole time, you could, and you'd get a more precise answer, but
Right.
It's fine if you round early. Yeah, good question.
Cool.
So part A, we've got our formula. And now the nice thing, and remember, I think I said this before, if there's a part B, and C or something, it almost always involves the work you did before. So don't make it harder on yourself. So now it says this tells you also, so okay, read the directions. I've been bad at that. Use part A to approximate the number of pythons captured or killed in 2017. And when it says approximate, we're going to round to like the nearest whole number, just because we're talking about snakes. So it's like, if they captured half of a snake, that's a bit, they can't kill half of a snake, right? So we're going to round, it's kind of like humans as well. Like we're going to round to the nearest whole person or snake. So using this model, I want 2017. So first I have to figure out T. T is going to be 2017 minus 1995. Okay. So this is, it should be 22 years. So now that I know that, this is like, should be cake, right? This should be good. So we're going to just plug and chug here. P of 22 is going to equal 20 e to the 0.21 times 22, right? And if you're doing this in a calculator or in Desmos or whatever, just make sure that whole multiplication like is in the exponent, right? And so, and maybe this is confusing because it's a decimal in times, but okay, this is like times, right? Okay, so when I did this and I round to the nearest whole python here, I got about 2,030 pythons. Oops. And maybe we should have tried, like, maybe at the very least, we could update these notes just to the current year. I bet these notes were like made by the professor in 2017 and she's just left it ever since, which is also fine. But I'm realizing maybe if I teach this again in a year, that this is some little thing I could do to just update if the book isn't updated by then. So yeah, and we could have calculated this, right? Add 5 more years. You could put 27 in there and see in 2022 if this was actually accurate. It was a study published in 2012. So, I mean, if it continued to be true, we could get how much in Florida Everglades, how many snakes were captured and killed. Or killed, sorry. All right, cool. And 2,000, that just sounds like a lot. And that seems like, and there's still more. Like, I'm just very, I guess maybe they're easy to mate and have babies. I don't know, but that's freaky. That just freaks me out. But if you're into snakes, hey, there you go. You had a little fun for today. Okay. So now we've got something that's more like, I think this is going to be decay or something like that. Yeah. So we have here radiocarbon dating uses the model. Q of T is this. Yeah. So see how they give us this equation. So they don't give us Q0. Oh, yeah, they didn't. I don't think they gave, or maybe they will give it to us, but they did give us K. This number is K. And notice how it's negative, right? That means this is an exponential decay problem. Yeah, Jakob, I would agree. Sharks are probably way more dangerous, but they probably don't capture or kill as many. And there might not be like an equation, and they could make that equation with that study, right? So yeah, but that is true. Okay, so they have this equation. Q of T is Q naught e to the negative 0.000121 t for the amount of carbon-14 remaining after T years, where Q naught is the original quantity of carbon-14. Okay, and carbon-14 I think is just radiocarbon. I'm not I don't really know, I guess. So, okay, part A says a sample collected from cave paintings on an archaeological site. We're getting like super historical lately in these problems. In France shows that only 2% of the carbon-14 still remains. How old is the sample? So we want, and ew, that was a bad like T, but we want T equals what? We want to know what is T? And they told us that 2% of the carbon remains. So, so what this is, this tells us that Q of T has 2% of Q naught of the original. And what that means, 2%, as we all know, is 0.02. So this is 0.02 of, well, okay, and maybe I don't need to write of, I can just write Q naught. So our Q of T is 0.02 of Q naught. So in this case, this is a bit weird, right? But there's two ways you can solve this if you're not liking this first way, but let me explain the first way, right? So the first way is that we don't know what Q naught is. We don't have this value, right? But because we're told that there's 2% of that value left, we can say, okay, 0 to Q naught equals Q naught e to the negative 0.00020121 t. And this is our formula. And now we can solve for t, right? So I can say, but watch what happens here. And maybe this will be crazy to you. We divide by Q naught. That's what we would do first. But when we do that, notice how it cancels on both sides. So really, when they told us 2%, that just means 0.02 is e to the negative 0.000121 t. And we can just solve this way. Right? So we can take log of both sides or natural log of both sides. And remember, this exponent, the whole thing comes in front, right? So we whole thing in front. So I get, and natural log of e goes away. So I get negative 0.000121 t is just equal to ln 0.2, right? And so, okay, I apologize. And maybe I'll write ln of e is here. But again, this just becomes times 1. So it goes away. And then I'll rewrite up here to solve. So then we get ln 0.02 equals negative 0.00121 t. And so we divide both sides by negative 0.000121, divide by negative 0.000121. And you'll definitely want to round this now. And so you'll get that t is approximately, so you have natural 0.02 divided by this big negative number. I mean, I get a huge number, but I got 32,331 if I'm just rounding to the whole number. And these are years. So that's pretty crazy that, I mean, but they were looking at cave paintings, right? Supposedly on an archaeological site in France. So, I mean, if you've ever, I've never been to France, but if you've ever been abroad, there's, I mean, granted, there's history in our country as well, but, or when I say our, I mean the US, but some of you are not necessarily from here. So, but I've been fortunate enough to have been to Rome before, and that is a very historical country. And I don't remember everything off the top of my head, but I definitely took notes and tried to remember, I journaled about what I did, because I went to all the historical sites and walked around, and we walked every day when we went to different sites. We walked probably 10 miles because you can just walk everything. And these buildings are, I mean, so old. Sometimes I thought, oh, this city is old, but it's not. Those buildings are truly, to me, like cave painting days. But I mean, granted, maybe that's not totally true, but it's very interesting, right? So to think 32,331 years, that's a lot, but at the same time, like this is supposedly a really long time ago. We're in year 2022 or, you know, whatever. So yeah, so it's interesting, I guess. But let me just explain the alternate way, like, to start this problem. We won't solve it all the way because it ends the same. But if you don't know Q naught, like Q0, you could just say Q0 and they tell you like this whole 2% thing. You could say Q0 is 100%. And then they tell you Q of T is 2%. So you could just have it be an actual percent, but then you would have like 2 equals 100 e to the negative 0.000121 t. And then you would divide both sides by 100. And then guess what you would have? You'd 0.2 equals e to the negative 0.000121 t. And then you'd be at the same exact place as we were here, right? So you'd continue as we did, right? So you can also, like, you could plug in any type of value really and say, oh, it's 2% of that value, but obviously 100 is a little bit easier and we can just keep the percents this way. So we got our total, we got how old is the sample? So this sample supposedly, right? This sample is supposedly 32,331 years old, which is wild. Now it says, part B says, find the inverse function and indicate what it calculates. So, okay, this time we're not really using part A, but the inverse function. So if we pretend we have Q equals Q naught e to the negative 0.000121 t, right? If this is our original function, what is recommended here? And you can switch, you can pretend. So if you really wanted, I'm not going to do this, but if you really wanted, you could pretend that Q was Y and the T was X. You could switch them and solve, just like the regular inverse, right? But I'm going to tell you for these problems, what I'm going to do is take this T and just solve the equation for T. And I'm going to say, don't switch letters because it just gets, it gets really confusing. I don't have X and Y to me. And then in the end you get, so basically we started with something like this, and this is, Q of T is what they gave us. And we're going to end up, we're going to do some work. I'll erase that in just a second. And then our final answer is going to be like, it'll be something like T equals blah, blah, blah. And really that's T of Q, right? So just like it's F of X, and then we write F inverse of X, instead of doing that, we're just going to flip-flop these and flip-flop these here, if that makes sense, okay? So if anyone doesn't like it, again, you can pretend they're X and Y, you can switch them, but we just don't write, we don't write the Q inverse of T. We don't write it that way, but you can. There's nothing wrong with that. Okay. So now we just solve for T. So we do exactly actually what we just did, but we don't have any numbers. So we leave all the letters. So I divide this side by Q naught, but this time I keep it. So I just say Q over Q naught equals e to the negative 0.000121 t. And then I say, okay, now I need to take log of both sides because, or natural log, right? Because I need to get that t in the front. So I say, okay, ln both sides. And then remember this exponent comes in front. So I get ln of Q over Q naught equals negative 0.000121 t, and then ln of E But again, I'm not going to write it. I'm just going to say, okay, this goes away. This is nice. But those of you that if you like to write it and then you like to just say this becomes 1 and it's gone, that's fine. And then we will divide both sides by negative 0.000121, divide by negative 0.000121, and it cancels that out on this side, right? And we're just left with t by itself. So I get t equals ln of q over q naught divided by, and I can put the negative wherever, but divided by 0.000121. Right. Now what you can do here, because this is this is fine, but you can actually take 1 divided by okay, maybe I'll write this in a different way. This is the same thing as negative 1 over 0.000121 and then times ln of all that, right? So if you just take this fraction, put this in your calculator, and you get a decimal, and instead of writing that long decimal in the denominator, and again, this isn't necessary, but it just looks a little nicer, you would get negative 8,000. Actually, or maybe I'll write t first. I'd get t equals negative 8,264.5 times the natural log of q over q naught, right? So this looks a little bit cleaner than that last answer, which again, I wouldn't be too concerned with, but I know your textbook, I think, wants you to get a number instead of a fraction, just because you can. And this actually is the same thing as saying equals t of q. So it's that inverse function. And then it does ask, indicate what it calculates. So I'll just kind of write this here. So we say, so first, maybe this was my final equation. And I'll say t of q, it calculates, what is it equaling? Well, it's equaling t, which is a time. So it calculates the time in years to reach some quantity q that we're given here, right? To reach a quantity. So maybe it's 2%, maybe it's 50%, maybe, q. And one thing to note here, again, this doesn't, you don't need to be saying this on tests or anything, but this is just something for you to note, that q and q naught need to have the same units. So, part A, we didn't even know what they were. It just said 2% of it, right? So we don't know if it's in grams, micro, who knows? But whatever their unit is, they would need to be the same. Oh, and maybe I should write this. It looks like I wrote Q1, but it's Q and Q naught. Okay, that's maybe a little better. So part C says, according to this model, what is the half-life of carbon-14? Okay, half-life is not trying to trick you. It's exactly what it sounds like. This means, what is the time to reach half, so 50% of Q naught, right? So that means that Q divided by Q naught is 1/2. Or 0.5. Okay, if you prefer 0.5, because 50%, right? But I always think of half-life. I always think 1/2. And so what that means is Q over Q naught is 1/2. So if use part B formula. Because we already solved it for T. So we have T equals -8264.5 times natural log of, and I'll put 0.5, but again, I do usually put 1/2, but no big deal because we already have decimals here. So, but if you don't have decimals, maybe it's nice to keep 1/2, but then your answer is totally going to be like approximate. So if we put this in our calculator, this tells us about 5,728.5, or you could say, if you want to round to the whole year, 5,729, and it's years. And what's crazy about this is that actually to reach its half-life, so this is how many years for its half-life, that actually doesn't sound like as many, right? 5,700. Okay, I mean, it's a lot of years, but that just shows you how exponential decay or growth, how quickly it grows. Because when you want to go down to 2%, it's not just double 5,000. It's not 10,000. It's 32,000, right? So it's just a little bit crazy to think about just how those functions work, right?
That's the exponential nature.
Exactly. Exactly. And so it makes sense. Like if you got like 30,000 and you're like, oh, it's only 2,000 less than what it was to get to 2%. Like clearly you did some work wrong. You know what I mean? So
Yeah.
It's also a logical thing. Yeah. It's good to think of it like that. All right. So now we're looking at specifically half-life models. Now, I'm not like, it is a thing, like a half-life model is something where you're only calculating a half-life, like when something, it starts from 100% and it goes down to 50, or maybe it starts at 100 or at 0 and goes up 50%. I'm not really sure if it's just growth or decay or which, but maybe it's just decay. Yeah, so we're going to look at these. There is a thing, again, called half-life models. And first, we're just going to talk about inverse properties, which we already know, but just a little reminder that if you have log base A of a to the x, then what's happening here is it's just equal to x, because if this base matches my base here, if I was to rewrite this whole thing in exponential form, it's just a to the x equals a to the x, right? So they cancel each other out. Same thing with if I have a, this is weird, but if I have a to the log base a of x, well, again, if I wanted to write this in, well, okay, maybe it's weird if I read it in log form, but if I wrote like this right here and it equaled something, this is saying a to something equals x. And then if I take log of both sides, maybe this isn't the best way to explain it, but what's happening here is the bases, again, the bases are canceling each other out, right? So maybe it's easier to see if you take log of both sides and log, that this comes in front and you have log base a of x, and then you say, yeah, again, maybe I shouldn't explain it this way. But what's happening here is these bases are the same. And so we're just they're canceling each other out and we're just taking what's left, right? Now what I do want to say about this is it looks different if there's no base. So keep in mind, if it's natural log, and you guys get this, but not everybody gets this, but if I have, I'm going to rewrite these with ln. So if I have ln e to the x, this is just x, right? If I have, not a, if I have e to the ln x, this is just x as well, okay? With log, if I have 10, if it's a 10, and I have 10 to the log x, this is also x. And if I have log of 10 to the x, it's x. So I want to point this out because you don't always have the base written in on logs, right? But these are all the same thing. So like this, 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 they're just different bases, right? So hopefully that makes sense. Well, and so now we're just going to see some examples. So in number 7, like A, B, and C. So 5 to the log base 5 of 3. I mean, hopefully you can see these bases are the same. So we're just going to get 3. And then we have log. So here's an example of the 10 one. Log of 10 to the 5x. Well, this is technically a base 10. We don't write it, right? But it's there. And so these cancel each other out, and we're going to just get 5x. And it's, well, okay, this, for this one, it also makes sense to say, using our properties of x of logs, we know that this 5x, it could come in the front, and then we'd have like 5x log 10, and log 10 is just 1, right? So then this is 5x, and that's how we get that, because that's just 1. And then this last one, e to the ln 2x. So again, this is just going to be what's inside here because they're both base e. So this is just 2x. Okay, so now we're going to look at another example of this equation with some exponential decay, and we'll solve for the exponent. So radon, different from radioactive carbon, which I think was the last one we looked at, but radon is an element obtained from the decay of radium. Okay, makes sense. Soils released potentially harmful radon gases into the air. Oh, okay, so radon 222 is an isotope of radon, sure, with a half-life of 4 days. Wow, okay. We have this A of X. So now, again, we're switching up our variables all the time here, but that's okay. So A of X is 25. So 25 must be that like A naught. And then 2 to the negative X over 4. But we want to write this in a form naught equals E to the KT. So we want to write it in our exponential decay that we have, but then with a base of 2 instead of a base of like 2 of E, 2.71, blah, 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 right? So what we need to do is we need to solve for X, and then we'll, oh wait, is it asking? Well, okay, maybe we don't have to solve for X actually. Yeah, so we technically don't have to solve for X, but why did I want to do that? Oh, I added a question in here that I took out. Okay, well, so maybe we won't do this, but first we'll write the model in this form, and then maybe we'll solve for X. Okay. So if we want to change it from this form to the new form, then we're going to start with, we know that A naught, we know that A0 equals 25, because that's the same from this equation, no matter what base we have, right? And so we can start with A of X is going to equal 25. And then we have, okay, so we have 2 to the negative X over 4. We want, I'm going to try to do some magic here. We want this to be E, right? We want this to be E. And so in order for this to happen, remember what we did up above. I'm going to do something freaky here. We want it to be E. So we want our base to be E, but right now our base is 2, right? Pretend X is 2 in that situation. So I'm going to rewrite, I'm going to use this guy right here, and I'm going to rewrite 2 as E to the ln of 2. Okay, so it's a little bit weird, but I'm going to write E, oops, not like this, okay. I'm going to write E to the ln 2, because that's literally equal to 2. And then the 25 stays, and then I keep negative X over 4. This is super weird, but this is totally fine. So now what we can do is we can just leave the E and take that ln2 and multiply it into the exponent, and then figure out like what that decimal is going to be. So then I get 25 and now, so next, the step here is going to be multiply the exponents together. And I'll just write them together first, and then I'll multiply it, and maybe I'll put this. So I'll have negative, so I'm combining negative x over 4 and ln2. So I have negative ln2 x over 4, right? So, and this is all an exponent, so maybe I should try to like write this. Okay, I wrote it really big, but maybe if I do this. Okay, now it's all an exponent. I don't know. I don't know if that looks any different. So now what you want to do is you want to get k, because like, look, we are so close to it looking like a naught e to the kt, but and t is my x. Okay, so this should be, okay, they messed up here. This should be an x. They isn't me. That's me. So we want k, and to get k, it's going to be this coefficient, ln2 over 4, and we just get, okay, so nothing crazy. So we're going to have 25 e to the, okay, ln2 over 4, and it's negative. So I get negative, I'm going to go 4 decimal places. So negative 0.1733 x. And if we want, let's actually pretend we messed up here and we want a of t in with kt. So, okay, here was our a of x. Then what we want to do to make it a of t is write 25 e to the negative 0.1733 t. And there it is. You could keep it in terms of x. I mean, I think, yeah, it doesn't really matter. And now one of the questions that I had wanted to answer that I, for some reason, took out of this, which maybe we can just do it real quick, or at least just discuss it, was like extra, I'll call it extra Q, extra question, would be how much time for the radon to decay to 5 grams, right? Oh, it won't let me write grams. Okay, to 5 grams. Now it starts at 25 grams, right? So, or we're assuming that's in terms, I think. So what we have here is, we would say we want 5 grams, and it's 25 e to the negative 0.1733, right? And then we would just solve for t, right? Divide by 25, take log of both sides, et cetera, et cetera. I won't do it all just because I didn't ask it, and maybe it's because it was like not rhetorical, but it's maybe unnecessary. But I don't know if your homework goes into this. So if it does, you'll end up with, okay, so you'd get 1/5. You'd get ln of 1/5 divided by negative 0.1733, whatever this is, or it's equal to t. And you would want to round that number and just say like this, and actually t in this case is days, right? It's not in like years or hours, or it's in days. So remember, it represents days. So if you get, I don't know what you'll get, but if you get like, 8 or 9 or whatever, it's days. Okay. So now we're going to look at some of these models, and we're specifically look at growth now. So those were some decay examples, and now we're going to look at growth. And I don't think you're never going to have to graph any of these, but I think they want to show in your book, like they want to show you images and see kind of what these like growths would look like, right? So for this first model, we can see it says exponential growth. This is what we typically were looking at, and exponential decay is what we were just looking at too. And this is what I was talking about. This represents a rapid growth, because over time, like you go from, maybe this is like 1 day or 1 year, and then this is like, 3 years, and you go from here all the way up to here, whatever this scale is, like you're just crazy growing, right? So it's rapid growth, I would say. And we're in quadrant 1. I mean, we're always going to be in quadrant 1. I don't know if that's necessary. But then we have logistic growth. Oops, that's supposed to be highlighter. So then we have like log growth. And what happens here, and this specifically is looking at like a population size. I don't know why over time, but I mean, probably because that's actually a really just traditional example of exponential growth is like population. And I think a lot of those examples are what you would see in your book, or like just as if you Googled like traditional examples of exponential growth or something. But if you have logistic growth, then notice what's happening. It's more of this like snaky type of thing. And it's kind of growing sort of not so fast, then like super fast, and it slows down and plateaus, So we have this kind of like little curve. And typically what happens with this growth is there's a maximum, like there's this, they're calling it the carrying capacity. So maybe like there is a maximum number of people, like, I mean, okay, this reminds me of an elevator for whatever reason, because, you can always, it always says like maximum capacity of this elevator is 300 pounds or 4 people or whatever it is, right? So maybe it's 3,000 pounds. 300 is probably not enough. Because you put 3 people in there, you're screwed. But I think of something like this that has a max capacity. So maybe like if it holds 1 person, it's here, but then like, and 2 people, it's kind of there, but then you double that and it's just like, it skyrockets to its max. And then you're like really close, right? And then you can't necessarily get past it. I don't, something like this. I don't know. Maybe the elevator is not a good actual example, but I just think that has a maximum capacity. Okay, so for this growth, we have the equation y equals c, and c is a constant, over 1 plus a, another constant, e to the negative bt, another constant. And notice that this little guy here in the denominator, this is the exponential term, right? Like the whole thing is an exponential term, I guess, but the exponential part, so maybe I shouldn't say term, but exponential piece is here, exponential part. And then A, B, and C are all positive constants. Now, they're all positive because we're specifically only looking at growth. And so when I say like E to the neg BT, B has to be a positive number, because if it was negative, then that would be positive and it would flip. Everything would be different, right? So now we'll look at like, only one example, I guess. We'll just look at one example. But there's like multiple parts. So actually, or maybe did I put 2? Oh, look at that. I put 2 examples. Okay. So we're having fun tonight. So the population of Los Angeles, P of T, in millions, can be approximated by the logistic growth function below. Okay, so some crazy person found this formula, and where T is the number of years since 1900. Okay, this is kind of nice because we're starting at a nice even zeroed off year. So like if it's 100 years, we're in 2000, right? If it's 50 years, we're 1950. If it's, you know, whatever, we can just count from zero. So it's kind of nice. And then we want to evaluate first P of 0 and interpret the meaning in the context of this problem. Okay, let's do that. So P of 0, this is no problem because I just substitute 0. So I'm able to do that. So it's 4 over 1 plus 40 e to the negative 0.07 times 0. So I know that this is going to be 4 over 1 plus 40 e to the 0, which is just 1. So this is 4 over 41, right? Which is approximately, wait, what did I do here? Did I do this wrong? Oh yeah, no, this is fine, this is fine. Sorry, I'm getting ahead of myself. So this is 0.976 million. Right? Are we in millions? Yeah, because we're in millions, right? So 0.976 million, which means that, and we need to interpret the meaning. Okay, so we have this decimal, and million is, it means, so million is the same thing as 10 times 10 to the 6th. So it means add 6 zeros. If I said 1 million, add 6 zeros to 1 after the 1, and that's $1 million or whatever, right? If I said million or 5 million, it just means times 10 to the 6th. So what does this mean? Well, we got 0.976. So this means that in 1900, because that's when we're at time equals 0, P of 0, and it starts in the year 1900. So in 1900, the population was about equal to 976,000, right? Because I would move this decimal place over 1, 2, 3, 4, 5, 6, because it's 0.976 million, which it's not yet 1 million, but it sounds like 0.9, it sounds like it shouldn't be 976,000. That's weird, but that's what it is, right? I'm going to take away that. So it's saying that in 1990, the population was about 976,000. And we're talking LA here. That's probably wild because, I mean, now it's probably, millions and millions. I don't really know, right? We live in Texas again. We don't know. We should do this for Austin though. Actually, that would probably be really wild. But the issue is you need to get this equation, and I don't know who writes that, it's not me. Okay. So part B is asking, use the model to approximate the population of LA on January 1st, 2020. Oh man, right before COVID hit, when times were good. No, I'm just kidding. Times are great, right? Okay, so we need to figure out what is T. Well, because, yes, you could say, okay, 1900 or 2020. Oh my God, I can't write. 2020 minus 1900. Yes, you could do that. But because it was nice and even in 1900, I know 2000 is 100 years later and 20 is 20 years later. So it's 120 years, right? So I know T is 120 years, and we want to approximate what this is. So P of 120 is going to equal 1 over 1 plus 40 e to the negative 0.07 times 120. Now be careful entering this in the calculator, but I trust you, it'll be fine. And when you do this, you should get about 3.96. Maybe I put one more decimal, 3.964 million. Which sounds about right. Granted, I was saying millions, but that's almost 4 million people. That's in 2020. That's kind of recent. That's probably true. I don't know. But if you got something like 99 million, okay, like you did something wrong. If you got like negative 0.5 million, okay, again, something wrong. If you got a number smaller than what we got up here, you know that that's not right because it's got to be growing, right? It's increasing. So you also want to use your logic for these types of things to make sure, you got it. Okay, part C. According to this model,
Google says 3.973 in 2020.
whoa, look,
Close enough.
and this was okay. Supposedly, this was in like 2018 or something, and it was a prediction. And look how accurate that formula is.
It is.
3.964 versus 973. I mean, that's pretty close.
That's in the ballpark for sure.
Exactly. It's ballpark. It's still, we're talking millions. So now we're talking like it's still 10,000 people off, but okay. In the scheme of things, it's good. It's pretty good. Okay. So according to this model now, in what year should the population reach 3.9 million? Okay. Well, we surpassed it here. So what this is telling you is that it's got to be before 2020. So what this tells me is when we calculate this, it like when it hit 3.9, it should be maybe 2010 or maybe just somewhere in like between, I don't know, 2000 and 2020 maybe or something, right? But okay, let's figure it out. So what we would say is we want this 3.9, this is our P of T. Right? So this is our answer. So we get 3.9 equals, and I have to look back at my equation. Oh my gosh, I wrote this wrong. I think I got the right answer. I didn't write 4 in the top. My bad. Hopefully, I mean, the number is still right, but okay. So it was 4 divided by 1 plus 40 e to the negative 0.071 or 0.07t. And what do we do? Okay, so we don't want fractions. So we need to multiply both sides by this denominator to get rid of it. So 1 plus 40 e to the negative 0.07t. So multiply by 1 plus 40 e to the negative 0.07t, right? And I'll multiply this 3.9 to both. So then I get 3.9, because that's 3.9 times 1, plus 3.9 times 40. So I got like 156 e to the negative 0.07t equals 4. Because on this side, these whole things cancel. Right? So now I subtract 3.9 from both sides. And I rewrite my formula. 156 e to the negative 0.07t equals 0.1. And then I divide both sides by 156 because I want that e alone so that I can take natural log of both sides. So I get e to the negative 0.07t equals 0.1. And this is where I take natural log of both sides. And when I do that, well, there they go. Here, wait, I'm gonna close it. And turn them down. It's okay. Okay. So we want this, we want this exponent to come in front. Whole exponent, and natural log of e cancels out, right? So we get negative 0.07t natural log of e, but again, this is just times 1 equals natural log of 0.1. So then divide both sides by negative 0.07. And I'll rewrite this nicer up here. So we get t equals natural log of 0.1 divided by negative 0.07. Oh my God, I forgot something. I forgot okay. in all of this, oh, that was not nice. In all of this, I forgot that this is 0.1 over 156. Right, so when I do that, okay, let me just fix this here. So this is 0.1 over 156. And then this is 0.1 over 156. Okay, better, right? Okay, better. I was distracted. Hopefully they're muted enough from you, but my dogs are barking like banshees over here. Okay, so now I get this approximate, right? And or not, or I get an approximate answer. So I got 105 about, right? 105, let's say. So what this is saying is in about 105 years, the population should reach 3.9 million, right? So, and before we were going 120 years. So that means in those 15 years, it only grew, it didn't even grow a whole million because it went 3.964. So maybe this is now a little bit off because it's growing a little faster than that in real life, right? But this is saying about 105 years, which we need to figure out what actual year. So what you could do is you just add 1900, or you could say, okay, 1900 plus 105, same difference. But this brings us to 2005. So population should reach 3.9 million. Right? That's what we just figured out here.
Is there a special way we need to be putting these into the calculator? Because some of my numbers are not coming up the same as yours.
Oh, okay.
I don't know what I'm doing wrong.
No, this is good. Which ones? Because if you tell me, I can try to enter it or and say, you know what I'm saying?
Mm-hmm. So when you did the 1 plus 40e raised to the negative 0.07 times 3.9, I got about 146.
Okay, let's see. Are you using are you using a scientific, a graphing calculator? What are you
graphing? I have a TI-84.
Okay. So let me so the only bummer, I don't have a full TI-84 that I could show you, but let me maybe share my screen with Desmos and we can talk about it. Oh, what did I do? Oh, okay. So give me a second.
Okay.
Because I'm gonna stop sharing. I'm a little nervous. Oh, could I get Desmos on the iPad? Probably. All right, let's by some miracle figure out where the
I don't know if anybody else is having the same
issue. No, so I plugged it in.
You basically can enter it exactly. I can explain it if you want.
Yeah, try to.
Well, you start with a fraction. You start with a fraction, right? That's your start point. So you use the alpha, and then the button next to it to the right to create a fraction.
Mm-hmm.
Then you put the on the numerator. You put the natural log. Where was it? Yeah, then you do it, and it automatically creates a parentheses, and then you put another fraction inside the parentheses. And then you just put 0.1 on the top and 156 on the bottom, and that's in the natural log parentheses. And then you I think you use the down arrow to go down to the denominator and put negative 0.07. And then that's what you do.
Okay, but I'm talking about the part where she multiplied it by 3.9 and she got 156. Is that what you're talking about?
That is when she distributed it's maybe that you can explain.
Okay, well, so here. So when I did that, I just did 3.9 times 40. Are you seeing my screen?
Yeah, I can see it.
Okay, so this was what Michael was just explaining, right?
Yeah.
to get the 156. So we had something like, 1 plus 40 e to
Mhm.
the blah, negative
0.07.
0.07 t, okay, we had something like this times 3.9. Now, okay, the calculator can't do times the t part, right? So you might have been entering this as well, but I was taking 3.9, distributing it to the 1, so I got 3.9. And then I was doing 3.9 just times 40, and that's how I got the 156. And then I put it in front of the E, blah, 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 and I didn't use anything else. Does this make sense?
Well, see, I was putting it exactly how you have it in blue, obviously without the T. And that's how I got
But see, that's not going to be right, because that's actually so that's not going to be right, because that's as if T was 1.
Okay.
And we don't know what T is. So you
Okay.
you can't just take the variable, because what it's doing is it's multiplying by this whole thing. And so now let me go back to sharing wow, if I can figure this out. Jeez. Okay. Let me go back to sharing my iPad. Again, if I can find, when you lose a tab. Okay. Oh, we've got it. We're in. Okay. Oh, there's a buddy.
Yeah, that's my dog.
Oh, yeah. Oh, mine are just ready to play. Okay. So like what we're looking at here. Oh, did I lose my marker? Nope, we're good. Okay. This 3.9, I only distribute it to the numbers, not to the, so that, and is there somewhere else where that happened? Because if that's true, that might be what we did.
Yeah, there was somewhere else, but I think it was the problem of 4, but I'll have to maybe.
Yeah, let me know. I mean, we're gonna have time. We're almost finished here. So yeah, if you find it and you see it again, we can go through it just to point out where that is, right?
Okay. All right.
Okay.
Thank you.
Yeah, of course. And thank you, Michael, and everybody. We're all helping each other. This is what we do. Yeah. Okay. And no, that I appreciate it. There's nothing to be sorry about. Okay. So explain what happens as time increases without bound, and therefore so we want to explain what happens as time increases without bound. So T goes to infinity. And that's what the carrying capacity of this model is. So what the point they're making is, as T is going to go to infinity, for exponential growth, like a normal exponential growth, that thing is going off to infinity. It's going crazy, right? But in these cases where we have like logistic growth, there's going to be this, they're calling it the carrying capacity, right? And there's going to be this capacity. And so what is happening here? So let's look at our equation again, because I have to scroll up too much to get it. So it's 4 over 1 plus 40 e to the negative 0.07 t, right? This is our equation. And notice what we want to focus on is we want to focus on the t bit, the exponential part. So if we focus on this and we say what happens, y equals e to the negative 0.07 t. Like what is going on here? Well, this is actually, so why am I saying as t goes to 0? Oh, here we go. So we want as t goes to infinity. So t goes to infinity. So this is actually equal to 1 over e to the 0.07 t, right? Because the negative exponent makes it a fraction, right? So what's happening is this number, e to the 0.07 t, as t gets bigger and bigger and bigger, this number gets bigger and bigger and bigger. Just goes to like off to infinity, right? But what's happening, that means that this is approaching 1 over infinity. And if you remember from like other things we've seen, right, in equations, 1 over x, and as x goes to infinity, that actually, and if you think about it, like 1 divided by 10, that's 0.1. 1 by 100, 0.01. 1 divided by a million, 0.000001, right? So as that number gets bigger, our actual whole fraction gets smaller. So this is decreasing. Okay, this is decreasing. And so it's approaching 0, right? So I'll say approaching 0. So maybe a nicer way to write this in general is to say this approaches 0 as t approaches infinity, right? And that means if this approaches 0, what I just highlighted here, that means this whole thing approaches 0. So this approaches 0, like 40 times 0, that's 0. And so the denominator, the whole denominator then approaches, and maybe I need to like find some different type of color here. We'll need this. So that means this whole thing, this approaches 1 plus 0, which is just 1. And the numerator is 4. So this tells us that P of t approaches 4 over 1 plus 0, which is just 4 as t goes to infinity. And what this means, based on the equation and based on whatever was calculated in whatever year this was created, right? This means that this 4 represents 4 million people, right? That's what this 4 represents. So this means the population of LA cannot sustain over 4 million people based on what this is saying. That's their capacity, right? Granted, okay, I'm sure right now they're hitting it or they've got it, but it's interesting because somebody calculated like this is going to be too many people. We're going to have to start kicking people out of LA. And you know what? They're probably just coming here to Texas. So do we want that? Do we not want that? I don't know. But yeah, so like the study, the statistics, the people, whoever was studying this, you know, they determined that there is this formula for the population growth, and it has a capacity, you know, theoretically, but you know, realistically, I don't know how accurate that is. Oh, I think, okay, I'm realizing now the extra practice is what I started to explain earlier and didn't finish solving. So oops, my bad. Okay. So let's see. Okay, hopefully part D. I mean, hopefully that's good. Now, note 10 is refer to this radon 222 example earlier. So this is, I must have just taken these pieces and changed them to later. Okay, back in business, except now, this time my iPad dropped too. So how much fun was that for everybody? Who became the professor? Okay, I'm back for now. Let's see if we can just get through this. Okay, shoot, am I not sharing my screen? No, aren't I? Yeah, okay. Ooh. Can you all hear me?
Yeah.
Oh, whew, all right. I'm like just waiting for it to drop again. Right. Oh, and Lauren was the professor. All right. Thank you, Lauren, for taking over my duties. Okay. So let's try to finish this. So what I was solving here is exactly what part A is asking down here. So let me maybe just try to rewrite a little bit of it. Okay. So the radon equation that we had, A of t, it was 25 e to the negative 0.1733 t. And we wanted to figure out when is this equal to 5. So what we did, we divided by 25 both sides to cancel that out. And we'd get 1/5 equals e to the negative 0.133. And then this is where I would take ln of both sides. And I am going to skip, I mean, I explained this before, so I'm kind of, if there's questions, let me know, but I'm just writing what we get, right? So we get this, and then we divide both sides by negative 0.1733. Right? And so what do I get? Let's see. So t is going to equal natural log of 1/5, well, negative divided by 0.1733, whatever that is. Now, hopefully we can all agree on this, but I actually have to calculate it real quick because I'm not confident that I calculated the right thing before. So let's double check. And maybe you've already got it. 1733. Okay. Oh, maybe I did do it right. So I get about 9.287. And then if I want to think about what does this represent, it's how much time it takes. And remember, we were in days. We were in days in this problem, not years, not minutes, not hours, right? We were in days. So this is about, I mean, maybe you could say about 9 or 9 point, maybe we'd round to only 1 or 2 decimals, but about 9.3 days, maybe between 9 and 10 days, something like that, right? In order for it to go from 25 grams to 5 grams.
I mean, would you just say 10 days?
Yeah, I guess by day 10, right? But if you, I think in this case with days, we can use decimals because it would be like 3/10 of the way through the 10th day we're done, right? So it's okay. But if you said 10, or 10 days, I'd accept either. It's not the same as like a human snake, like you're not capturing or killing half of a snake. It's a whole. We're going to do whole snakes. But this can have it be a decimal. And the last bit says how much time does it take for any amount of radon 222. So now I'm just saying any amount, like A0 e to the negative 0.1733 t to decay to 1/3 the initial amount. So what this means is if I want 1/3 of the initial amount, I'm just going to, this is the whole thing where I'm just going to say, well, okay, you could either think of an example and you could say, okay, suppose A0 is the initial amount, suppose it was 30 and I want 1/3 of that. So 10, right? And you could do this, or you could just know that these amounts don't matter. And we just want a ratio of 1/3. So 1/3 equals e to the negative 0.1733 t. And notice that if I used an example amount, if I just divide both sides by 30, I get 1/3. So this is why we could kind of skip, we could kind of skip this example step and just say, I want 1/3 the initial amount. So I just want 1/3. Or you could think of it as like A equals 1/3 of A naught, right? So you'd have 1/3 A naught equals A naught e to the negative 0.1733 t. You would divide both sides by A naught or A0, and then you'd still have 1/3, right? So again, so many different ways to think of it. But once we're here, then we take natural log of both sides. And we basically do the exact same steps that we did over here, right? And we are going to get negative 0.1733 t is equal to natural log of 1/3. I mean, yeah, that's what we get. And then we divide, so we get t equals natural log of 1/3 divided by negative 0.1733. And again, I don't trust my previous calculations, so let's try it. I'm getting about 6.34 or something. So maybe I'd say, I'd say about 6.3 days or between 6 and 7 days, or 7 days, if you wanted to just be exact, because in 7 days for sure, this will decay to 1/3 of the amount.
We got 0.639.
Did I get, wait, what'd you get? Sorry.
I got 0.6339.
0.63. Okay, maybe I did this wrong. Let me check real quick.
Oh no, I know why, because I did 1.7. Never mind.
Okay. I was like, I just put this in Desmos. I think I did it right, but then of course I cleared it, and I'm like, I would have to type it again, but no big deal. So okay, so now we have, now we have our time here, and these are all the exponential or logarithmic growth decay models that we're going to be seeing. So the good and the bad news is that next class, we are going to talk about right triangles again. We are not going to do any trig. Oh, I'm lying. Trig is going to happen next class. So trig is making a comeback. So for those of you that didn't like it, I'm very sorry. There is some trig. It's not, but to me, it's the easy trig, I think, because it's just like sine, cosine, and tangent. Yeah, don't be too upset. It's just like sine, cosine, and tangent, and like SOHCAHTOA. It's really back to our SOHCAHTOA. But for those of you that liked it, be happy next week in chapter 7. So next week, we're looking at chapter 7 sections, like 7.1, 4, 2, and 3. We're going in a weird order, but it's for a reason, I like to think. And again, I combined. So if you look, I'm going to save this. Oh, dear God, please tell me that's saved. Okay, thank goodness. All right, good. Done, saved. So I will post that tonight. But next time, remember, for unit 3, for whatever reason, maybe I was feeling some type of way, I'm not sure. Joseph trig is coming back, and so there's set. Yeah, sorry about that. Next week there'll be a little bit of trig, just a little, some right triangle trig. Okay, but notice how 7.1, 7.4, 7.2, 7.3, they're all bunched together. We are not obviously doing all of those notes in one night, but we are going to do them all in 1 week. So we are supposed to get through all of these next week, which this is kind of a long one. So maybe it's not. maybe I can do it. But so that will all be all the notes just for next week. And this week they were all kind of organized in this, right? And I'll make sure those get posted. But as for tonight, I'm actually going to end, I am going to end class a little bit early. Because I have to pick today has been a week, right? I'll just tell you a little story if you're interested. If you're not interested, question of the day. I decided, I'm being lame with these questions, I think maybe, but okay. I was really into, we're finally like seeing other humans this weekend since I'm feeling better and I tested for COVID and I don't have it and whatever. But, I really wanted to make like a nice cheese board. So tell me your favorite cheese. And if you don't eat dairy or anything like that, this is fine. Give me a vegan cheese. Give me a whatever. If you want to give me the jam that you like on the side, tell me that. If it's not even a cheese that goes on a cheese board, again, I don't care. One of your favorite cheeses, tell me what you like. I love Gouda personally. Gouda and Brie are like my two favorites. I've done a baked Brie before with some fruit and it's just real good. But I want to read about all the cheese likes, right? And again, if it's not, up to you. But my fun story. So thank you guys. And I'll post the notes later. If you have questions on homework, again, let me know. And if you need it to be extended, let me know. But otherwise you are free to go tonight and I'll probably leave here in just a few minutes. But for those of you that are interested,